The Voyager spacecraft, launched in 1977 to explore the outer planets, was operated by the Jet Propulsion Laboratory, JPL, in Pasadena, California. Despite what their names might imply, Voyager 2 was launched first on August 20, 1977, followed by Voyager 1 on September 5, 1997. Though launched later, Voyager 1's trajectory was designed for a faster trip, allowing it to overtake Voyager 2 while exploring the outer solar system. Originally planned to visit only Jupiter and Saturn and expected to last only 4 to 5 years, Voyager 2's mission was extended to include a visit to Uranus and Neptune after successful flybys of the two target planets. This expansion was made possible by a rare alignment of the planets occurring once every 175 years, which allowed Voyager 2 to utilize the gravitational assistance of each planet to propel itself to the next. While Pioneer 10 and 11 had previously conducted flybys of Jupiter and Saturn in 1973 and 1974, respectively, the Voyager missions were equipped with advanced instruments designed to conduct more comprehensive and detailed investigations of these distant worlds. As both spacecraft took advantage of the rare alignment of Jupiter, Saturn, Uranus, and Neptune, they were able to conduct a multi-planet tour and further exploration of 48 moons and the unique systems of rings and magnetic fields of each planet with minimal fuel requirements. After exploring the outer planets, both Voyagers started exploring interstellar space far beyond the initial planned mission. The initial plan of a Saturn-only mission turned into the grand tour of the solar system and went further into its current interstellar mission. With NASA JPL's engineers and scientists' extraordinary foresight, each Voyager carried 11 instruments, which was crucial in the success of its missions. Thanks to the Voyager's imaging science system, which includes narrow-angle and wide-angle cameras, they gave us stunning and vivid images of the planet and its satellites, which have made an enormous impact today. Scientists could determine the planet's physical properties with their radio science system. They were also able to investigate the local and global energy balance and atmospheric composition, and measure the atmospheric properties of the planets with the infrared interferometer spectrometer and ultraviolet spectrometer. A magnetometer is on board to analyze the planet's magnetic field and its interaction with the solar wind. The plasma spectrometer examines the microscopic properties of plasma ions, also serving as a low-energy charged particle device to measure their fluxes and distributions. A cosmic ray detection system is installed to determine the origin and behavior of cosmic radiation. Furthermore, a planetary radio astronomy investigation system is included to study radio emissions from Jupiter. Lastly, to measure the planet's surface composition and study the planet's magnetosphere, a photopolarimeter and plasma wave system are also present on both Voyagers. The high-gain antenna, HGA, serves as the workhorse for communication, beaming data on the planets, moons, and rings the spacecraft encounters back to Earth. It operates on 2 frequency channels: the X-band channel at about 8.4 GHz, which carries science and engineering data, and the S-band channel at around 2.3 GHz, which only sends engineering data on the health and state of the spacecraft. The Voyager spacecraft uses a 3.7-meter or approximately 12 feet diameter gain antenna, effectively communicating over vast distances. Back on Earth, the Deep Space Network aids in receiving signals from Voyager using its large antennas, like the 70-meter or 77-yard dish, enabling communication despite the immense distance of about 24.4 billion kilometers or 15.2 billion miles from Earth. The radio science system, RSS, piggybacked on the HGA to probe the physical properties of these celestial bodies. It is a crucial component of the telecommunications subsystem investigating the giant planets and their moons. The RSS enables radio science investigations of the masses, densities, and low-order gravitational fields of celestial bodies. Meanwhile, the Cosmic Ray Instrument, CRS, and Plasma Science Instrument, PLS, focus on different particle populations. CRS focuses on high-energy particles to understand the solar system's environment. It includes a high-energy telescope system, HETS, low-energy telescope system, LETS, and the electron telescope, TETS. Designed to detect energetic particles like protons or electrons from the galaxy or Earth's sun, the CRS measures mega-electron volts, or MeV units, which dictate the energy of charged particles, such as cosmic rays and solar particles. High-energy charged particles can be a significant hazard to spacecraft and astronauts, so understanding these particles' energy distribution and flux is crucial for mission planning and spacecraft design. The Plasma Science Instrument, or PLS, is designed to detect the lowest energy particles in plasma, analyze particle speeds and directions, and study the boundary between our solar system and interstellar space. It also studies solar winds at our solar system's fringes. The PLS plays a significant role in understanding the dynamics of planetary magnetospheres and provides valuable data on changes in plasma waves as the spacecraft approaches and enters interstellar space. Magnetospheres are protective regions surrounding planets whose magnetic field dominates, protecting them from the solar wind and other space phenomena. These magnetospheres are crucial for studying interactions of plasma waves and magnetospheric plasma resonances at outer planets like Jupiter, Saturn, Uranus, and Neptune. The data collected by the Voyager Plasma Science Instrument has greatly enhanced our knowledge of the heliosphere, the interaction between our solar system and interstellar space, and the characteristics of the interstellar medium. The Low-Energy Charged Particle Detector, LECP, measures ion distribution, offering scientists valuable data. This device is crucial for studying charged particles in various sources like the solar wind, cosmic radiation, the sun, planets, and interstellar space. Mounted on a rotating platform, it utilizes two solid-state detector systems, the Low-Energy Particle Telescope, LEPT, and the Low-Energy Magnetospheric Particle Analyzer, LEMPA, for particle detection and analysis. Scientists study low-energy charged particles to understand the behavior and characteristics of charged particles in different environments. The information obtained from this device is significant as it helps researchers gain insights into the composition, energy levels, and movement of these particles. This data is essential for advancing our knowledge of space physics, solar activity, and the interactions between celestial bodies and their surrounding environments. The Low-Energy Particle Telescope, or LEPT, is optimized for detecting low-energy particles and forms a vital part of the LECP experiment on Voyager. It captures and analyzes particles like electrons, protons, and other heavy elements in the space environment surrounding the spacecraft. The LEPT plays a crucial role in identifying and studying these particles, offering valuable insights into the composition and dynamics of the space environment encountered by Voyager. The Low-Energy Magnetospheric Particle Analyzer, or LEMPA, is another critical subsystem of the LECP specifically designed for magnetospheric measurements. It is optimized to analyze particles within the magnetospheres of celestial bodies such as planets and moons. The LEMPA plays a vital role in studying the low-energy charged particles in these magnetospheres, aiding in identifying the shape and characteristics of magnetospheres around planets like Saturn and Uranus. At the end of the Voyager spacecraft is the movable scan platform that houses 5 optical sensing instruments, including 2 cameras. The Imaging Science Subsystem, ISS, comprises 2 black-and-white television-type cameras. One has a low resolution of 200 mm or 7.9 inches wide-angle lens, and the other has a higher resolution of 1500 mm or 59 inches narrow-angle lens, sharp enough to read a newspaper headline at a distance of approximately 1 kilometer or 0.62 miles. In front of each camera is a rotating filter wheel containing 8 filters. By combining images with different filters, imaging scientists can create accurate visual color photos from the black and white camera. Photopolarimeter, or PPS, is a powerful tool for studying the gas giants. It uses a small telescope and special filters to analyze light scattered by particles in their atmospheres. This allows scientists to identify the chemical makeup of those atmospheres. The PPS also looks for auroras and lightning, which can reveal information about a planet's magnetic field and electrical activity. The instrument focuses light through filters, separating colors and blocking light depending on its polarization. A special detector then amplifies the faint signal for analysis. The PPS captures data as Voyager moves around a target, acting like a single pixel camera with an adjustable view. The infrared interferometer, spectrometer, and radiometer, or IRIS, are 3 separate instruments. First, it acts as a thermometer, allowing for the observation and measurement of heat energy emitting from an object. Second, it acts as a spectrometer to identify various elements, molecules, and compounds that may be present in an atmosphere and on the surface of a body. Third, the separate radiometer measures a body's reflected infrared, visible, and ultraviolet light. The ultraviolet spectrometer, UVS, on the Voyager spacecraft is a specialized type of light meter sensitive to ultraviolet light emitted by atoms and ions during specific physical processes. It looks for particular colors of ultraviolet light that certain elements and compounds are known to emit. The UVS instrument is crucial for studying various aspects of planetary atmospheres, such as determining surface composition, analyzing atmospheric structures, measuring the loss rates of volatile gases, and investigating the compositions and dynamics of atmospheres. 3 radioisotope thermoelectric generators, RTGs, mounted end-to-end power the spacecraft, converting heat from radioactive plutonium into electricity to keep the Voyagers operational on their long journey. The RTG units served as the central power sources for the mission, with each RTG weighing 37.7 kilograms or 83 pounds, including about 4.5 kilograms or 10 pounds of plutonium-238. Using 24 pressed plutonium-238 oxide spheres, it can provide enough heat to generate approximately 157 watts of electrical power, halving every 87.7 years. Voyager's got 2 long booms sticking out from it. One boom carries science instruments, while the other, a 1,311 centimeters or 43-foot-long fiberglass rod, is all about magnetism. This magnetic boom keeps the spacecraft's electrical stuff far from the magnetometer instruments at its tip. Why? Electrical things can mess with those readings because the magnetometers are super sensitive and need super accurate readings of magnetic fields. These magnetometers measure magnetic fields, including those of faraway planets, their moons and rings, and even the edge of our solar system where the sun's influence fades. While both Voyagers shared a large set of scientific instruments, some additional instruments were specific only to each spacecraft. Voyager 1 carried the planetary radio astronomy, PRA, and plasma wave antennas, PWS, designed to study radio waves emitted by the gas giants. These instruments provided valuable insights into the magnetospheric plasma resonances of those planets. On the other hand, Voyager 2 was equipped with a micrometeorite shield to safeguard its instruments from the hazards of dust and particles in space. It also had an optical calibration target, which helped maintain the accuracy of its onboard instruments. The Voyager spacecraft, including Voyager 1 and 2, are equipped with a sun sensor crucial for navigation and orientation in space. The sun sensor is designed to detect the sun as the brightest object in space, guiding the spacecraft to rotate until it aligns with the sun, ensuring the antenna is facing Earth. However, there are times when the sun sensor is temporarily blocked. This can occur during planetary flybys or when capturing specific targets. In such situations, Voyager also has a gyroscope. This device can track the spacecraft's rotation for several hours, providing essential data when the sun sensor is temporarily blocked or when Voyager rotates to capture images. The Voyager project balances the power usage between the heaters and the instruments. The transmitters on Voyager 1 use 200 watts of power, and the engineers have been turning off instrument heaters to conserve energy. This has caused the instruments to operate at much colder temperatures than designed, but amazingly, they are still working. Eventually, the power will run out, and Voyager 1 will no longer be able to transmit signals. This is expected to happen within the next few years. NASA engineers already estimated that its nuclear-powered generators, NPGs, will likely die around 2025. However, the radioisotope thermoelectric generators, RTGs, may be able to continue giving power to the scientific instruments of the spacecraft up until 2036. But barring any unforeseen anomalies, the spacecraft will go silent by 2030 at the latest. Reliability, redundancy, and reconfigurability are critical to a long-lasting space probe. The Voyager mission benefited from all three. The probes were designed with tight engineering and fabrication standards, redundant components, and the ability to be reprogrammed to work around failing parts. The Voyager spacecraft has 3 different computer systems, each playing a crucial role in its operations. The Computer Command System, or CCS, acts as the nerve center of the Voyager. It boasts dual 18-bit word processors with 4,096 words stored in non-volatile plated wire memory. It consists of 3 dual redundant computer systems per spacecraft, with the first system being nearly identical to that flown on the Viking mission. The primary function of the CCS is to manage and control various aspects of the spacecraft's operations. It is of utmost importance to the Voyager mission, enabling the spacecraft to execute commands, process data, and make decisions autonomously. It ensures the proper functioning of the spacecraft systems, allowing it to navigate through space, collect scientific data, and communicate with mission control on Earth. The redundancy built into the CCS provides reliability and resilience, essential for the spacecraft's longevity and success in its mission. The Flight Data System, or FDS, is a computer system responsible for controlling the spacecraft's instruments, collecting and formatting data, and transmitting it back to Earth. It is the primary data handling system for the Voyager probes, working in conjunction with a single 8-track digital tape recorder, DTR, to manage data storage and transmission. Please think of the data system as Voyager's memory bank, storing precious information about our universe's mysteries that scientists will analyze and decode on Earth. These solid-state and digital tape recorders store and relay invaluable data to Earth. FDS plays a crucial role in the Voyager mission by managing the vast amount of data generated by the spacecraft's scientific instruments, ensuring that valuable information is stored and transmitted back to Earth for analysis and study. This data has led to numerous significant discoveries about the solar system, including the discovery of active volcanism on Io, a satellite of Jupiter, and the detection of a marked change in the plasma environment, which suggested that Voyager 1 had entered interstellar space. Similar to how a pilot navigates an aircraft through turbulence, the Attitude and Articulation Control System, AACS, maintains the spacecraft's stability and orientation. It ensures that the spacecraft is correctly pointed toward Earth for communication and tracking purposes, and its instruments are correctly pointed toward their targets. The AACS ensures that Voyager stays on course, even amidst the cosmic currents of space. It uses gyroscopes, accelerometers, and star trackers to determine the spacecraft's orientation and thrusters to adjust its attitude, position, and trajectory. It is a critical system that maintains the spacecraft's communication link with Earth. Without the AACS, the spacecraft could not preserve its orientation correctly, communicate with Earth, or transmit data back to Earth. The propulsion system provides the necessary thrust for Voyager to maneuver and explore distant celestial bodies. It utilizes radioisotope thermoelectric generators, RTGs, to generate power for propulsion and onboard systems. Like a safety net, these backup systems provide reassurance and resilience, allowing Voyager to push the boundaries of exploration without fear of system failure. Voyager has redundant backup systems for critical components to ensure mission continuity. These redundant systems act as fail-safes, ready to take over in the event of primary system failure. Each of these computer systems on the Voyager spacecraft is custom-built and serves specific functions essential for the overall operation and success of the mission. The redundancy built into these systems ensures reliability and fault tolerance. It allows the Voyager probes to continue functioning effectively even after decades of operation in the harsh space environment. The Voyager spacecraft's software was initially developed in assembly language with some Fortran components. Fortran is a powerful tool for scientific and technical computing. Initially designed for ease of use compared to complex machine languages, it excels at numerical problems in weather prediction, engineering, and physics. Over time, it gained other features, making it adaptable to modern computing needs. While not the newest language, its efficiency, extensive libraries, and rich history make it a mainstay in high-performance scientific computing. Assembly language offers a trade-off between ease of use and performance. While complex and requires deep hardware knowledge, assembly code directly translates to machine instructions, making it exceptionally fast and adaptable for specific tasks. This low-level control allows programmers to optimize code for particular hardware or efficiently implement algorithms. The onboard software manages overall operations, monitors the health of the probes, and communicates with other systems. NASA personnel use the ground software to plan the mission and analyze the data that comes back. Assembly language, which is closer to machine language, was used because it is closer to the fundamental binary code. Assembly language is a low-level programming language that directly represents machine code. An assembler converts assembly code into machine code, which the computer executes. Translating Fortran into assembly code is more complicated than translating assembly code into machine code. This process involves a compiler, a program that translates high-level programming languages into machine code. The compiler breaks down the Fortran code into smaller pieces and then translates it into assembly code. An assembler then translates the assembly code into machine code for transmission to Voyager through the Deep Space Network. Voyager's computers function on an interrupt-driven system where the software executes regular instructions until an interruption occurs. Updates for Voyager trigger an interrupt signal upon arrival. The central computer halts its operations, processes the update instructions, uploads the new code into memory, adjusts the necessary bits, and then resumes normal operations after verifying the code's accuracy. This meticulous process ensures seamless integration of updates into Voyager's system. The spacecraft's low-power transmitters, large directional antennas, and specific radio frequencies with minimal interference help ensure successful communication. Currently, Voyager 1 is 15 billion miles, or about 24 billion kilometers from Earth, and operates at a meager power of 160 bits per second. Engineers must adjust for the distance and faint signal by aligning all antennas at the Deep Space Network. While challenges exist, the team's meticulous approach and specialized technology enable them to send instructions and receive data from the Voyager spacecraft. This allows for continued exploration and data transmission from these probes. The NASA Deep Space Network, DSN, provides support for numerous deep space, highly elliptical Earth orbit, HEO, and low Earth orbit, LEO missions, including those currently operational and those in the developmental phase. Additionally, the DSN assists in ground-based radar and radio science missions. Notable missions supported by the DSN include the Mars Reconnaissance Orbiter, currently orbiting Mars and aiding other Mars missions. New Horizons, which conducted a flyby of Pluto in 2015 and is now en route to a Kuiper Belt object. Juno, currently orbiting Jupiter and studying its atmosphere and magnetic field. Cassini, which completed a 13-year mission exploring Saturn, its rings and moons, before its decommissioning in 2017. And Galileo, which studied Jupiter and its moons from 1995 to 2003. Furthermore, the DSN assists Earth-orbiting missions, such as the International Space Station, or ISS, the Hubble Space Telescope, and various Earth-observing satellites. Notably, Voyager 1 and 2, having ventured into interstellar space, continue to maintain communication with the DSN. These three Deep Space Network facilities are roughly 120 degrees apart around the globe. They are the Goldstone Deep Space Communications Complex in Barstow, California, United States, the Madrid Deep Space Communications Complex in Robledo de Chavela in Madrid, Spain, and the Canberra Deep Space Communication Complex in Canberra, Australia. The strategic placement ensures that at least one antenna can always communicate with any spacecraft as the Earth rotates, no matter where it is in space. DSN played a massive role in the success of the Voyager missions to Uranus and Neptune. Without the DSN's ability to receive data signals from these distant spacecraft, those missions would not have been able to transmit their valuable scientific findings back to Earth. The aging Voyager spacecraft poses a significant challenge for engineers who rely on outdated documents and manuals from the 1970s to address the issues they encounter. Since it was initially planned as a 4-year mission, they did not anticipate the complications arising from the spacecraft's extended duration in space. Additionally, radiation exposure poses a risk of hardware damage, further complicating repair efforts. The Voyagers have made many discoveries and defied expectations, exploring the depths of our solar system and venturing into interstellar space. Despite challenges and aging hardware, NASA's engineers prepared the Voyager spacecraft and continue to push the boundaries of space exploration, ensuring these iconic probes keep transmitting valuable data back to Earth. Thank you for joining us as we journeyed with Voyager 1 and 2. We will see more about their discoveries and challenges in the following videos, so remember to subscribe, and hit that notification bell for more updates on their interstellar travels. What do you imagine Voyager 1 and 2 have encountered beyond our solar system? What cosmic enigmas might they be investigating now? Please share your thoughts below, and until next time, let's keep exploring together.